To the April meeting of the Central Florida Astronomical Society, once again meeting virtually. We were talking briefly in the board meeting about when will we be able to get back together, and we do not have an answer for that. We're hoping sometime this fall. Everybody's getting vaccinated, and things are either going to get much better or they're going to get much worse, and we'll just see what happens. And when we know, you will know also as well. So thank you for joining us here again via Zoom. So tonight's program, we got a good program. We're going to talk about black holes. Everybody likes black holes. Then we're going to have some of our mini programs, member astrophotos and sketches, curated by Derek. I'm going to spend just a minute on the moon, if you'll permit. Then Derek's going to talk about the death of Pluto, or maybe not. And then Bill Castro, our own member, is going to talk about stargazing in the Orlando Nebula. And I've seen his slides, and that looks like a good little mini presentation as well. Just some reminders as we get going. Our new website is live. If you missed it last month, CFAS.org is up and going. We've greatly streamlined the website. It's more of a sort of seeker-oriented website if you're interested in CFAS, to learn about CFAS and how to join in the meetings and so forth. Once you're a member, we want you to join our Groups.io mailing list. Groups.io has a nice little portal where we have all of the important documents. If you want to know what the CFAS bylaws are, that sort of thing, or spy on the board meeting minutes, you can find them there. Also, we're collecting good YouTube videos and links for beginner tips and things like that. For the last time, I will not bring this up again. We still have some Royal Astronomical Society of Canada observing guides, and we also have some Astronomical League calendars that are still available. We still have 2 books and 5 calendars. Get a hold of me at my email address there, or via president@cfas.org. Will also work if you're interested, and we can arrange to meet at say the Lake Mary Starbucks or something like that for a book and calendar swap. Also, our monthly reminder, Sharife is always on the lookout for astrophotos, or also just any member news. If you're doing something interesting, let her know, and she can promote that as a CFAS activity. Send that to her at her email there. That would be great. By the same token, outreach, if you are interested in doing outreach or volunteering for an event, let Lynn Ward, our outreach coordinator, know, because he is our outreach meister on that sort of thing. Upcoming events, of course, we've been a little shy because of course, the pandemic, and it's very difficult to do things public. But we do have a couple of good online programs. Actually, we don't. The planetarium is doing a couple of good online programs. I've got some Zoom links here. I'm going to paste those into the chat box as our main program gets going. So if you don't remember the WN_GW-KRZ blah 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 blah, don't worry, I'll paste those in for you. They look like pretty interesting. I don't know if Derek wants to hop in or not. Derek, you have 3, 2.
All right, yeah, I'm here. I'm here.
All right.
Hello, everybody.
About these?
So we're partnering with several of my colleagues in different areas of the United States to put together some cool programs. The program that we're going to be doing on the 23rd of April at 7 p.m. actually is involving 2 of my friends, Feather Maish and Alexis. And they are going to be talking about the star knowledge of the Lakota people over in the Dakotas area, if you will, of the United States, and very, very rich history in understanding the night sky. And it's our way to kind of honor indigenous cultures here in the United States and their knowledge of the sky. So this is something that you definitely, if you're interested in ethnoastronomy, cultural astronomy, history of astronomy. I know we have a lot of members here that are interested in that. This is definitely something you won't want to miss out. And then on May 14th at 7 p.m., we're also having another program. My friend Catherine Hunt, she is with the Ingram Planetarium in North Carolina. She put together a really great program called River of Heaven Asian Astronomy. She is of Korean descent, so she is going to talk about, specifically Southeastern Asian cultures, predominantly Japan, Korea, and China, but other areas as well. So if you're interested in learning about the amazing contributions to astronomy in this area of the world, that's a great program too. And also May is the Asian Heritage Month here in the United States, National Heritage Month for Asian cultures. So if you're interested in checking that out, those are the links. It is required registration, just like you would a normal CFAS general meeting. And if you have any questions, shoot them over to me, and I'll be happy to do that. Anybody's welcome. It's free. So be sure to share that out. Thank you so much.
Thanks, Derek. And I'll paste those links into the chat box here in just a couple of minutes. So as my dad used to say, let's get this show on the road. Trisha, I'm going to turn it over to you. And then Amy, you can, I'll just stop sharing when Trisha's done talking, and you can take over and you'll be ready to go.
Thanks, Richard. Hello, everyone. Thank you for coming to our April meeting. So tonight we have Amy Oliver. So let me tell you a little bit about Amy. She is currently the Public Information Officer for the National Radio Astronomy Observatory. She's also a SciTech expert and communicator. She lives in the lower Sonoran Desert with 2 cats, 48 hummingbirds, 2 thirsty desert rabbits, and 1 aggressive roadrunner, which we'll have to ask her about for sure. She previously worked as the Public Affairs Officer for the Whipple Observatory at the Center for Astrophysics at Harvard and Smithsonian, and also in public affairs for large space and satellite technology organizations. Amy has been telling the stories of constellations since she was 5 years old and comes from a family of astrophotographers, astronomers, and scientists. She's obsessed with astronomy, satellite technology, and whales. We will link her social media in the chat, so go follow her on her space adventures. If anyone has a question to ask Amy this evening, please make sure to put your question in the Q&A tab at the bottom of your Zoom screen. So without further ado, let's welcome Amy Oliver.
Thank you so much. So the things you guys find out about me online, I'll go ahead and pop this up. So I think you guys should be seeing me, a picture of me with my name. Richard, are we good?
Yes, you're good.
Excellent. So it all worked out in the end. So thank you everyone for having me tonight. So as Trisha said, I'm Amy C. Oliver. Here is a very lengthy list of the things that I am doing right now. So if you don't mind, I'll give you a sort of short rundown as well, so you have a little more background on me. So as Trisha said, I am the Public Information and News Manager for the National Radio Astronomy Observatory. I'm also the Public Information Officer for ALMA in the North America base. So we actually have multiple public information officers for the ALMA telescopes. I am a contributing writer to Earth Sky. I'm going to give a plug about that in a little bit, so keep your ears open. And I am a social media contractor to the Noir Lab, which is formerly known as some other things. And I'm also continuing to be public education principal investigator for the Whipple Observatory, which is part of Smithsonian Astrophysical Observatory. I am also a new fellow of the Royal Astronomical Society this year. I am on the Outdoor Lighting Code Committee for Tucson and Pima County, Arizona. I am on the Tucson Sign Design Review Committee. In Arizona, I'm a board member at large in the Historical Astronomy Division of AAS, and I'm a NASA JPL Solar System Ambassador. So yes, the joke at the bottom is, actually no, I do not have a life. If you can find me one in space while you are out looking through your telescopes, please let me know about it. So today I went ahead and let's see, that's not gonna go. All right, click. Today I actually changed the title of my presentation. So originally we were talking about a bunch of bad holes, and now I wanna talk today a little bit about their really bad habits. So in case you guys didn't know, we're halfway through Black Hole Week. So NASA every year hosts Black Hole Week. So a lot of really exciting things have been happening in the news. And you've probably been overwhelmed by all of the pictures and information that are going out about black holes in general, and maybe not noticing that a significant amount of news has come out just this week. Actually, I might look a little tired tonight because I was up pretty early dealing with news about black holes. So what you're looking at right here on the main screen is there was some new research out yesterday from the Netherlands Research School for Astronomy. And astronomers, so if you guys are not as familiar with the history of black holes, astronomers have studied active galaxies since the 1950s. So an active galaxy means that it's a galaxy that has a nucleus or a compact region at the center of the galaxy that is emitting what we maybe used to think of as unusually high quantities of electromagnetic radiation. This energy isn't released in visible light. So that means we can't see it with our eyes. You can't see it with your small backyard telescopes. We can't even see it. Previously, when I was at Whipple Observatory, right, we have the MMT there, which is the 14th largest optical telescope in the world, and we still can't see it. Okay, we'll talk about why that is in a little bit. So instead, astronomers have been observing this kind of very violent activity in the universe in radio waves and gamma rays. For a significant portion of their observations. These active galactic nuclei, or those compact cores at the center of active galaxies, swallow matter in this very messy way. For anybody out there who's seen Stand By Me, you know, that 1980s movie that was like a Richard Bachman book, really Stephen King. Okay, there's this really disgusting pie eating contest that happens in this book. And in the movie, it was actually really well depicted in the movie. So while this is going on, so while all of this activity is going on, just like a pie eating contest, they are just spewing and emitting all sorts of electromagnetic radiation in the radio, the infrared, ultraviolet, and X-ray. So all the way across the electromagnetic spectrum. Now, some other things that this new research has learned about black holes is that they're not all the same, right? They're not the same kind of eaters. So when you're in a restaurant, if you're a people watcher, right, you see those people who you watch them get their food and you think you're going to age 20 years waiting for them to finish a meal, right? They're really slow eaters. So slow eating black holes accrete matter at a very slow pace. So we're talking, you know, millions of years. They can also be really greedy. So there are black holes out there that are just gobbling up matter and then accreting it at this really rapid pace, and they're growing really large into these supermassive black holes because they're accreting matter so quickly. And we're actually going to use the word cannibalistic in a little bit here, so that's a buzzword. It's a lot like my family at Thanksgiving, right? When the rolls come out, okay, that's the way I think of it. Like my brother walks over and then he walks away with like 15 rolls. And there's none left for anyone else. That's what these black holes are like. So then there's a third kind, and they can be legitimately emaciated. They are accreting matter at such a slow pace that we really don't, we don't know why, right? So we're going to talk a lot about that too, the we don't knows. The big thing is that a lot of these black holes don't necessarily emit radio jets, right? So what you're looking at here in this picture is you're seeing these jets, jets coming out of there. And at the National Radio Astronomy Observatory, right, we're looking at things in radio. And so it's really important to look at black holes and active galactic nuclei in many different wavelengths. And the other thing that causes problems, and I told you, I promised I would mention this to you, is that if there's star birthing activity present, and radio jets are not being emitted, it's even harder for us to see what's going on. And that's why it's so important to look at them in different wavelengths. So this is a black hole, right? We don't have a lot of pictures of black holes, you know that, so we'll talk about that in a second. Black holes are these voids in space, okay? So they're a point that is so dense in mass that they create this gravity sink. And it's all of this gravity pulls into this very small space. And roughly certain types of supermassive black holes, you know, it's like a 4-mile wide jar and you've got to fit Earth in it a few thousand times, okay? And that's really what you're jamming into this small space. And so they're really dense mass-wise. But the reason that they can be really difficult to detect in space, we talk about them as being invisible, but that's because the temperature is actually on the order of a billionths of a Kelvin. And so it's really hard for us to see things at sea, okay, with my little rabbit ears up here, see what's going on out there. They're invisible because we can't detect that heat, right? So we are waiting for something to heat up. We're waiting for energy to be released. That's why they're really difficult to detect. We can't see them straight on either, right? So we've got a number of problems. So black holes have these gravitational fields that are so strong that even light cannot escape. And we define black holes by this black sphere here, right? The singularity. Singularity is like no man's land. You don't want to end up here if you're a star. And you also don't want to end up here if you're a person. Okay, this is where time breaks down and space compacts. If you were in here physically, if you were in the singularity, you get, first you get stretched out on the event horizon and you're being pulled in by the gravitational pull. And, for me, that's great because I'm a hobbit and I could stand to gain a few inches or, a million. But then the next thing that happens is that time would actually start to break down and time would be moving very slow for you, but you would think it was normal. And then it would be like everyone was trying to break the barrier, right? So everybody would be going well over the speed limit to your view. So let's go back and talk about the event horizon for a second, right? So that's the threshold around the black hole where the escape velocity surpasses the speed of light. So escape velocity is what it takes to get out of a place, right? So on Earth, when we send a rocket into space, we have to achieve a certain escape velocity to get off of Earth. And when a hypervelocity star escapes the Milky Way galaxy, it has to achieve its escape velocity to get out of the Milky Way. Same thing here, except you would have to be going faster than the speed of light. And what do we know about that? No. Einstein, theorized, and we know you can't really go faster than the speed of light. So why we have been able to study these invisible beasts is because when matter gets too close, it gets caught by the gravity, right? So it gets caught in this gravitational pull. And it's a bit like a mutation to me between a spider's web and a Venus flytrap. So if you're the type to have nightmares by visualization, you're welcome. But if that matter then gets squeezed and then it gets stretched and it gets superheated and it becomes a part of this glowing disk of gas. Okay, so that's what we're looking at, that accretion disk in that image. So now we also have new observations of the black hole, a star pair called Cygnus X1. And we're going to talk about that in a minute because that's really important to this discussion we're having about how big something is and how much that accretion disk actually matters. So there are 4 types of black holes. I just raised 2 fingers. 4. I'm tired. I need more coffee. So those 4 types are stellar, intermediate, supermassive, and miniature. Okay? And the most commonly known way a black hole forms is by stellar death. Now, there are actually studies going on that we're going to talk about in a second that are challenging that theory. And so we're going to keep going back to this idea of we actually have no idea, right? Black holes are new enough to science in the way that we can actually truly observe them, that we are learning something new every week. Okay, so studies are coming out all the time and we learn something new every time we turn any kind of telescope at a black hole. So everything I tell you today could be wrong a week from now, which is actually great. And it's really wonderful to think about it in that way. So if we think about black holes being formed by stellar death, when a star reaches the end of its life, they mostly inflate, lose mass, and cool to become a white dwarf star. Now, if you're familiar with white dwarf stars, there's actually a new catalog out within the last year called the Extremely Low Mass White Dwarf Star catalog. And I recommend that you Google that. It's actually a really cool catalog. The guy who developed it is also famous for hypervelocity stars. And he talks about how they engage with each other in binary patterns. And so it's really cool to get to know that type of research, especially when we're talking about the end of a star's life. So the largest, by the way, of these white dwarfs, they're about 10 to 20 times more massive than the sun. And they have a destiny. And that destiny is to become either a neutron star, a super dense neutron star, or a stellar mass black hole. Okay, most stellar mass black holes, though, they're really difficult to detect. And that's for a significant number of reasons, right? Any number of reasons. There is a gas cloud surrounding the black hole, and that makes it difficult to find through radio wavelengths. It could be that they don't have jets, so any number of different things. And despite that fact, though, we do know that because of the number of stars that are out there that are large enough to produce a stellar mass black hole, that there are probably at least 10 million of them in the Milky Way and up to 1 billion of them. And so that's just another thing that we don't know and we still have to learn. And so, we're going to talk about EHT here in a second too, and that's why it's really, really important. So also we're going to talk a lot about supermassive black holes. So I don't want to ruin the Einstein part, but of course we know that they were predicted by Einstein's general theory of relativity. And they can have a mass, billions of times the mass of the sun. And so these monsters, okay, they hide at the center, the very center of most galaxies. So that's what the research tells us. And what you're looking at here is Sagittarius A, which is parked right at the heart of the Milky Way galaxy. So this is the beast that is hanging out. It has a mass of around 4 million suns. Okay, that's pretty big. It's not quite as big as the galaxy M87, which is the famous galaxy of photo, but it's also a lot closer to Earth, much, much closer than M87. And it's only 25,600 light years away, right? So that's pretty close. So our supermassive black hole, our residential supermassive black hole, is a lot more temperamental than M87 as well. So it gives us a lot of flares, it does a lot of belching, it does a lot of sneezing, it's really greedy and it eats a lot of stuff, okay? And no wonder it's so big. It has a lot of outbursts. It's really popular in science because all of this can happen in the single course of one evening of observing. And for radio astronomy, that's actually really cool because we can, there's so much activity going on, we can simply just turn in that direction and we get to see something very regularly, right? So we're constantly being able to gather information about anything that's really active in space. So these fluctuations, though, are why we don't have a picture of Sagittarius A yet. Okay, so hopefully that's going to be something that happens in the future, right? Especially with the Event Horizon telescopes. We always hope that we'll be able to collect enough data to reconstruct an image just like we did with M87. The really teeny tiny black holes, by the way, they're just theoretical. I have a colleague at Harvard, his name is Amir Siraj. He actually has theorized that there is a grapefruit-sized black hole hanging out where everybody thinks Planet 9 is. So keep your eye on science to see if they prove his theory right or wrong. And that's just, by the way, one more reason for me not to like grapefruit. So what you're looking at here is an artist's conception of how small and large black holes in both the nearby and distant universe form. So small black holes usually grow through accretion And large black holes usually grow through mergers in the modern universe. Okay, so you're looking here at the nearby and the distant universe. However, the opposite was actually true in the early universe. And this is a study that was done in the last year and a half by a scientist named Fabio Piccucci. And he has also figured out that there is less gas freely floating around the universe. And that's because it's been incorporated into multiple generations of stars, and existing black holes have just been gobbling this stuff up, right? They're very greedy. That's why we see a lot of supermassive black holes in the distant universes, because they're gobbling things up. So although the modern universe is not really this untapped reservoir of gas, and black holes have had a lot of time to grow, and they become these, epically proportioned things out there in the universe. And so they also do a lot of colliding. All right, so we also refer to that as a little bit of cosmic cannibalism. So there's that buzzword I mentioned to you. So they grow by merger, and they can continue to become larger. So in the more nearby universe, or the modern universe, we're seeing that supermassive black hole happen by cannibalism. They basically eat each other. So when we're talking about table manners, I mean, that's like my brother being 5 and elbowing me at the table, or stealing my food, I guess. I mean, never mind, we're not going down the cannibalism road. All right, so we have arrived at that one black hole. Okay, since we're talking about multiple wavelengths, I want to hop back in time a couple of years. This past weekend, we celebrated the 2-year anniversary of the Event Horizon Telescope constructing the first ever image of a black hole, which is the supermassive black hole, that monster at the heart of galaxy M87. So we saw this amazing image, this orange donut, and it was pretty exciting. But here's the thing about what we were looking at, okay? We were only seeing this one part of the story. So we're phenomenally excited about this, and we were able to indirectly observe the black hole by the way of its shadow. That's all that we were really seeing. So I really hope you guys all maybe didn't see the news today, so I get to lay this out for you. But we're gonna check out this video that NRAO just released today as a part of big news that came out, and then we're gonna talk about what just happened. See if I can get this to play. There is no sound, so don't worry. Okay, so, oops, let's see. Okay, so what we were looking at the end of the video, take a second and look at this. You can really look at what we are seeing. And I hope as you were watching the video, you were kind of getting the magnitude of what was going on in this study. Okay, you know the image at the bottom left. That's everybody's favorite image that of M87 and seeing that shadow and seeing the black hole. All of these other images, what they're showing is structure and impact on the surrounding environment. So I don't know if you guys happened to notice in the video, but what the video was talking about is how far that impact is actually stretching across the galaxy itself. So we have this supermassive black hole at the center of the galaxy, and the galaxy itself is only 60,000 light years across. But if you remember from the video, there is activity 100,000 light years across. And so that's what we're seeing when we actually start to look what Hess, Magic, and Veritas we're seeing, and that's the gamma ray. Okay, so we're actually seeing that activity. So each of these different telescopes, so even though EHT does include, ALMA, for example, ALMA did take additional separate observational data to help this. So when you're seeing that in the upper left, so we're actually seeing that structure, and we're seeing that between 1 light year from the core out to 100,000 light years in distance. That's how far this black hole is able to impact its environment. And it's pretty phenomenal to think about it that way. And so as we've been able to start seeing all of this different structure, we're getting a really good understanding of just how powerful black holes can really be, and especially supermassive black holes. So as scientists begin to turn their telescopes and their collaborations on different black holes, we're going to start seeing a lot of different information. And in that vein of poor table manners, I mean, look at these images, right? Like, it's like throwing food. It's like a food fight for one. Only the black hole is throwing food. Nobody else gets to throw anything back, but we're getting to watch this. And I think perhaps one of my favorite images here is actually the Hubble Space Telescope. And that's the bottom middle here. And it's very interesting to be able to look at that and kind of see there's this bright dot in the center, and that's the galaxy, right? So we're like actually seeing M87, and then we're seeing this visible light structure so far away from the actual core of the galaxy. So now why did we do this, right? So at the bottom of that image was the spectrum. And you can actually see all of the different telescopes involved listed on there. I'm sorry, this is a little bit little, but I'm glad everybody can see it on their own computer screens. So we all know that there is visible light, right? And that's only a small part of the full electromagnetic spectrum. And we're not going to stay on this for very long, but I just wanted to point out, for example, that we use infrared like the Chandra X-ray and NuSTAR, because sometimes dust and gas clouds obscure visible light that can be seen in the near, mid, and long infrared. And here is my personal promotional plug, okay? I mentioned to you I'm a contributing writer for Earth Sky, and there is an article from me out on Earth Sky this week because I just wrote a pretty cool, totally unrelated to this article about recent research involving studies in the mid-infrared. And I don't want to ruin the surprise, but you guys really need to watch out for it by the end of the week because it's really, really cool, okay? So do you know what? We've actually known about black holes for a really long time. So we're talking about all of this cool research that just happened in the last couple of weeks, in the last couple of years. But we've actually known about black holes since 1781, technically. So in 1781, this guy has been ruining bets, okay? In 1781, Messier cataloged M87. Only he said it was a nebula at the time, and so it took a little bit of time for us to get around to actually calling black holes, okay? But he's not the only one. I want to point out he's not the only one who has ever questioned what a black hole is or what it looks like, okay? So quasars are large supermassive black holes at the center of a galaxy, and they are so active that they tend to outshine the stars that are actually in the galaxy. Okay, so rotating around the galaxy. They have accretion disks around them that are a lot like Saturn, but a lot bigger. And they tend to be at the center of galaxies that are really, really, really far away from us. The difference between quasars and a blazar is actually the angle of the stream. So as you're looking at this image here, you see if the stream is straight up, okay, that's actually a radio galaxy, which is not shown here. If the stream is angled slightly and towards us, then it's a quasar. And if the stream is angled directly towards us, straight down the middle, it's a blazar. So that's why in this image, you're looking at the blazar face on, okay? Recently, and I cannot remember the date on this, scientists actually had an entire conference about the classification of active galaxies and black holes, including quasars, blazars, and radio galaxies. So really, we haven't completely settled on this yet. And I think just for the sake of time, I had a video I was going to show you guys about quasars and blazars. Trisha or Richard, do I have time to show a couple of minutes of this, do you think?
Yes, you do. Take your time.
Awesome. Maybe. Play. Thank you.
On the planet that I'm from, this is known as toilet paper. It's toilet paper. But I'm not here to discuss personal hygiene today. This is about astronomy and how we name things. As shapes go, this roll of toilet paper is pretty straightforward. From almost every angle, it's a cylinder. But if you look at it directly like this, then it's a circle. I know, your minds are totally blown, and you're probably wondering when we're going to start talking about astrophysics, but imagine for a second that we called things by different names depending on what angle we saw them from. If I were holding it like this, we'd call it a roll of toilet paper, but if I showed it to you this way, we'd call it a sanitation ring or a hoop of cleanliness or something. That wouldn't make a lot of sense because we get to study toilet paper rolls from whatever angle we want to, when we want to, which was probably not very often. But in astronomy, we don't get to do that. We have to study the objects that we see at whatever angle they happen to be relative to our planet, at least so far. We can't like pick them up and spin them around yet. So sometimes in astronomy, we'll call the same object a different thing depending on what angle we're viewing it at. And that's the case with quasars and blazars. And it makes a lot of sense because while quasars and blazars are technically the same thing, they look very different from our perspective, and they allow us to understand the universe in very different ways, which is pretty cool. Quasars and blazars are both types of active galaxy nuclei, meaning that their galaxy is big enough and has enough energy, and the black hole at the center is massive enough that it forms an accretion disk around it, and then from its center accelerates a massive amount of stuff in a single jet at a 90-degree angle from the plane of the galaxy. These active galaxy nuclei are the brightest persistent objects in the universe, and that's even more true when you look at them straight on. Quasars are a type of active galaxy nuclei viewed at an angle, and there are lots of them, and we've studied them for decades. Blazars, on the other hand, are the same type of active galaxy nuclei, but they're much more rare because they are when we're looking at the galaxy nucleus straight on its head, like a flashlight shining into our eyes. This leads to all sorts of weirdness because the particles accelerated out of the black hole are often moving at close to the speed of light, while they're also emitting energy at the speed of light. When studying blazars, we get to study in practice why throwing a baseball from a train moving at the speed of light would not violate Einstein's relativity. Blazars create all kinds of weird effects like Doppler boosting, which makes them look even brighter than they are, sometimes brighter than all of the stars in the galaxy they originate from combined. So just because of the angle that they're facing us at, they appear to be completely different to us and act in different ways than quasars. Now, with all of the fun stuff in science, the difference between quasars and blazars remain controversial, but many astronomers have concluded that they are in fact the same thing, just seen at different angles. Quasars are what we see at a glancing angle, while blazars are just quasars that we see looking straight down the jet. Hopefully, I help clean up some of that confusion. Thanks for watching this episode of SciShow. If you have any questions or comments or ideas for us, please leave them on Facebook.
Okay. So I always really like to show that video when I'm talking about that difference between quasars and blazars, because then you understand they're really not different. And so the interesting thing is that we go back to that understanding that we as scientists are always still trying to learn something new. And we're still trying to figure out what are we going to call these phenomena. Plugging that article again from me later in Earth Sky. I actually love something new that's out there with a new name. So in addition to Messier, right, of course we know Einstein. So Einstein first predicted black holes in 1916 in the general theory of relativity. So even though Messier already technically knew they were out there, Einstein was the one who had to predict them. There were some other guys, by the way, in the 18th century that sort of came up with the same idea, and I can't remember their names right now. But so this idea has been going on for a really long time, where different astronomers and different scientists and physicists are starting to try to work out this sort of issue with the universe and how space and time were working together or working against each other, and where these gravity sinks might exist. So this has been going on for a very long time. Now in 1964, some 6,070-ish light years away in the Cygnus constellation, we found Cygnus X1 in X-ray. Okay, so think about it. We already knew that this region was there, but what's really interesting about the different types of astronomy, so we're talking about radio astronomy versus X-ray astronomy versus gamma ray astronomy, is that we always have to rediscover the same regions. Okay, so for example, Veritas, rediscovered the Crab Nebula in about 1978 because they found gamma rays, tera-electron volt gamma rays coming from the Crab Nebula. And so that became then the standard candle for gamma ray astronomy. And not Veritas, excuse me, I just made a mistake, but it was a gamma ray telescope at the Whipple Observatory, precursor to Veritas. So back in 1964, there were Geiger counters that were launched into space, and they detected these cosmic rays coming from this region that we know as Cygnus X1. Okay, we now know today that those cosmic X-rays were caused by black holes. So back then, scientists actually still disagreed about what it was. So you're all familiar, I'm sure, with Stephen Hawking, and many of you probably know who Kip Thorne is. And at the time, they had a big, huge argument about this. And Stephen Hawking bet Kip Thorne that the signal wasn't actually from a black hole. And Stephen Hawking had to eat his words and concede, but not until 1990. So that's 26 years later. Stephen Hawking admitted that he was wrong in 1964. So back then, back then, of course, we were using Geiger counters. And then in 2016, scientists used the Very Long Baseline Array, which is one of my new telescope systems at NRAO. And remember, it's only been 12 days, so don't ask me a lot of questions about the VLBA. I will find you Dave Finley, who is their PIO. But so they used the VLBA in 2016, and we're just now learning some new things in 2021 based on those earlier measurements and with the application of new understanding. So a lot of scientific research takes a really long time, right? We need multiple measurements. We need to compare our data. We ask people to replicate that study to make sure that our scientific understanding is correct, because the one thing we don't want in science is a retraction, right? We're all about finding out new things over time. So from 1964 to 1990 is great. We learned some new things. Stephen Hawking could very happily admit that he was wrong in 1964, but we don't want tomorrow to be the day that we have to say we were wrong. So this is kind of what the network for VLBA looks like. And astronomers got a new look at Cygnus X1 using this array. So this network of 10 radio dishes stretches across the United States. It goes from Hawaii to the Virgin Islands. It's forming basically a continent-sized radio dish. So when you think about, for example, EHT, you know, we have that worldwide collaboration, and we have this very large radio dish by connecting all of these telescopes together. So there are actually multiple collaborations like this, where there are radio telescopes all over the world. You know, Europe has the VLT, which is the Very Large Telescope. And that is involved in VLBI, which is Very Long Baseline Interferometry, right? So we have a lot of things going on. We have a lot of these collaborations with different telescopes. And so in 2016, like I mentioned, the VLBA tracked radio bright jets of material spewing. Okay, so think about like somebody eating and talking at the same time, and food is just spewing out of their mouth, right? Okay, so this is what's going on for about 6 days. In this region of the sky. And that's about the time that it took for the black hole and its companion star to orbit each other one time. So 6 days. So we're watching this black hole eating while talking and spewing food crumbs for 6 days. And those observations actually helped scientists to get a clearer view of how the black hole's position in space had actually shifted over the course of its orbit. And that in turn helped them to re-estimate the distance to that region and to that black hole. That's really important, because when they re-estimated the distance, they found that they were wrong. So scientists originally thought that it was 6,000 light years away, but the new estimations and the new data told them it was actually 7,200 light years away, so 7,200 light years away. What that means, or what it implies, is that the star in that region actually has to be brighter than astronomers previously thought. Now, what that means is then too, it's probably bigger. And they're guesstimating that it is about 40.6 times the sun. Okay, so we're looking at 41 solar masses, okay? That means the black hole has to be more massive in turn because of its gravitational tug on that star. So in order for the relationship that scientists were seeing to occur, both of them had to be bigger than we originally thought. Now the black hole then is estimated to weigh about 21.2 times the mass of the sun. So it was originally thought to be about 14.8 solar masses. So that's significantly bigger. So we're talking, you know, a little more than 6 additional solar masses to that black hole. And so that's really important in our understanding of this black hole that's just so close to Earth. That's really big. And so that new mass measurement of that black hole is so big that it actually challenges our understanding of massive stars that collapse to form black holes. And so scientists are now having to go back and rework theories and change the way that we look at how everything works surrounding black holes and how they form. So back in 2020, and this is the last thing I want to show you today, which is 2020 seems like a decade ago, okay, because of the pandemic. I swear when I tell people about 2020, I think 5 or 10 years ago. So back in 2020, I worked with my colleague Ido Berger at the Center for Astrophysics and the European Space Organization to push out this news that they legitimately watched a black hole eat a star. So I'm going to show you this video, this animation of what that looks like, what a death by spaghettification actually looks like. I'm going to play that again, just because I want you guys to kind of think about what you're seeing. You're seeing a very violent activity here. Okay, so what this animation is depicting is that star experiencing spaghettification as it's being sucked in to this supermassive black hole. And what you're seeing happen here is what we call a tidal disruption event. So in this study, using both the Very Large Telescope and the New Technology Telescope of the European Space Organization, these astronomers found out that when a black hole eats a star, just gobbles it up really greedily, it launches this blast of material out, and that's what you're seeing. You're watching this blast of material. I want to play it again. I'm always just amazed watching this. Doesn't matter how many times I watch this animation. So this happens, okay, because the energy released as the black hole eats up the stellar material propels that debris, just propels it at enormous speeds outward. So we talked about this at the very beginning of the presentation when I was talking about that new news from EHT, looking at M87 in different wavelengths. Okay, so this material is being propelled out at almost the speed of light. And so it can be viewed in many different wavelengths: radio, X-ray, ultraviolet, gamma ray, even visible light, right? So we're getting to this point that all of this material is superheating and getting to this point where we can see it in all of these multiple different wavelengths. And that is what a tidal disruption is when all this material starts blasting out. So this research is helping us to better understand black holes and how matter behaves in these extreme environments, and where gravity is so extreme that it is just ripping stars apart and accreting this matter and then shooting particles back out. This, by the way, is actually called AT 2019 QIZ. And scientists said that it could act as a Rosetta Stone for interpreting future tidal disruption events and really starting to understand anyway, what's going on. So what was supposed to happen was that the Extremely Large Telescope, which was supposed to start operating about mid of this new decade, and the pandemic may have changed that date, I'm not sure, but scientists are going to be using the Extremely Large Telescope to start looking at fainter and faster evolving tidal disruption events. So these events that we haven't really been able to observe in real time, so that they can better understand black hole physics. And so the one big takeaway I'd like you to take today, as I'm going to play this again, is legitimately how violent black holes are and really how messy they are. They are perhaps the messiest of all objects in the universe, at least in my opinion. And I'd also like you to think, I mentioned if you were to get pulled into a black hole, what that experience might be like, and here we have it. So we're looking at what that experience might be like. And thank you so much for having me today. And I'll take questions now, if that's okay.
Amy, can you hear me? It's Trisha again.
I can.
Okay, so the first question comes from Bob Vogel, and he is asking, is the pace of eating based on available matter or some other intrinsic characteristic?
That is a great question, Bob. So there are a couple of different ways that we can look at this. And the first thing I want to tell you is that scientists are actually still researching this information, right? So they have theories about what's going on. So let's go back and talk about what researchers found announced just yesterday, right? That we have a few different types of eaters. So we have those ones that are emaciated, and then we have that are not really eating anything, and we don't really know why. And then there are the ones that are really eating really slow. And then there are the ones that are really greedy. So what we know from Fabio Picucci's previous study is that those, those supermassive black holes that are really greedy. So supermassive black holes are going to be the most greedy of all black holes, right? So those ones that are accreting matter very quickly and are very greedy exist in the distant universe, where they were able to accrete matter because it was really abundant. So there was a lot of matter around to suck into the black hole. So in the nearby universe or the more modern universe, we don't have as much material just hanging out because stuff has already formed. Okay, so, you know, if there were a black hole, say, sitting right in the middle of the solar system, we already have planets, right? So we already have planets and stuff. We don't have gas and dust just hanging around. So in that vein, right, there was a lot of material in the distant universe for them to accrete. Now, if they start to do a merger, imagine if a supermassive black hole and a supermassive black hole said, hey, let's eat each other. That would be terrifying. I'm not sure what that kind of cosmic cannibalism would look like. But so right now, scientists are sort of, what the idea is that it is based on the type of material that is available in the surrounding area. And so it's a really good question to ask.
Awesome. Okay, so next question is also from Robert Vogel. He's asking, why are black holes cold? Wouldn't the crushing of matter create heat?
It does create heat. You're 100% right. But so we've got that singularity in the middle, right? And that is a gravity sink. So what happens is we have that accretion disk, right? And that's where all the heat is, right? So the singularity is this gravity sink. That's that no man's land. You don't want to be in there. And scientists have actually started doing studies where they're trying to look into the center of a black hole to sort of figure out what's going on. Why is it so cold? Why is it this billionths of a Kelvin temperature in the center when we have all of this heat in the accretion disk, right? Because that is why we can. That is why we can find an accretion disk when we're not looking head on, is because of all of that heat of that material. And so you're asking a question we don't 100% know the answer to right now because we can't actually get in there. But to go back and kind of, I don't want to skip over your question because I really wish I had an answer for that. But it's all about that difference between we've got that singularity and we've got the gravitational pull. And when you get into that singularity, it's like all bets are off.
Okay. So our last question comes from Frank Kane. He's asking, if a black hole were small enough, could things cross its event horizon without being spaghettified?
I do not know the answer to that, Frank. But, and thanks for the great question, friend Frank. So when I mentioned Amir Siraj earlier, and he has that theory about the grapefruit-sized black hole. And in that theory, he actually has talked about why we have never noticed it before. Because it is so small, right, that it's got to be also emaciated. So you've asked a really good question that actually links back to what Bob asked before about eating, how much material they're accreting, right, and how they grow. So if we have this teeny tiny grapefruit-sized black hole and it's emaciated, then that means it's not actually accreting matter. And so it's very possible that if it actually is out there, if this thing is actually out by the Oort cloud, things might be passing by and we're seeing a disruption, right? So why there's a theory about Planet 9 is because we can see a disruption happening. Right, so so that's what theorists are talking about, is that we see something that looks like a disruption happening out there in the Oort cloud or near the Oort cloud, but we don't actually see what. And so it is possible, in theory, that there's a black hole out there that's emaciated and doing nothing. But until they figure it out, it's all the theory, and I don't have a really good answer to that, but I would really recommend that you Google Amir Siraj and get to know his theoretical research a little bit on that, because he has a number of theories about black holes, both supermassive black holes and small black holes, that will give you a good idea of where he is going theoretically and where he's pushing practical astronomers to go to as well.
Thanks for that, Amy. Well, thank you so much for presenting to us. I know the club really appreciated your time. So feel free to follow Amy. I linked her website and her Twitter in the chat for you guys to check out. And thank you so much, Amy. We really appreciate your time.
Thank you, Amy.
Thank you. I was so glad to be here. Thanks, guys, for the great questions.
That video was really awesome too. At the end, you could have just kept playing that. So I am going to abuse my executive privilege here. I could not ask a question in the Q&A thing because I am a presenter. It wouldn't let me type a question. So your question about why are black holes cold? My guess, and if you can't tell me why I'm wrong, you might can, but they won't let anything away, even light. Well, isn't heat light? Isn't heat electromagnetic radiation? So if it can't emit any, if the black hole itself can't emit anything, then it certainly wouldn't be able to emit any heat. And then of course, all the stuff around it is just hot because it's being so accelerated by the gravity field. Would that be close, maybe?
Maybe.
Maybe.
Right? I personally do not know the answer to that. And, but you're probably right, because once material gets into, so as we're talking about that, that's actually good. This is a good discussion, right? Because I talked about when you end up inside this singularity, time would actually almost cease to exist. You would slow down. Mm-hmm. And part of what makes the accretion disk visible is the speeding up and the heating. Right? So everything is being stretched out, sped up, and heated to a point that we can actually see it because it's releasing energy. So when it ends up inside of the singularity,
right,
it's going to slow down. And so all of that energy goes away and it's already gone. So there's nothing left to actually be able to see.
Cool. Yeah, I just remember Hawking radiation. Once you're in, the only way you get out is Hawking radiation. And that's, you know, longer than the universe is going to be around. And I am not an expert, but I thought I would throw that out just in case my guess was close.
I mean, I feel like black holes are cool to talk about, right? Because so much of it is still theoretical.
Right.
How to observe them. And what I'm really excited for is that research that's out there right now. And I wish I could remember who the principal investigator was, but they are legitimately trying to see into a singularity. So they're trying to look straight down the middle of a black hole to really get a good understanding of the physics of the internal components of a black hole rather than just understanding the accretion disk. So we know that the singularity is there and they're saying, okay, well, what if we could try to figure out like what's in there? Like what is needed? What's needed to figure out what's in there? And so, so I think it's really cool that they're attempting to do that so that we have a real answer rather than just a theory.
Cool. Yeah, you can't give a talk to the general public or do an outreach event. Somebody doesn't ask about black holes. So it's certainly a very interesting topic. And I hope our CFAS members learned something tonight. I learned quite a bit. And I'm going to say it again. I love that video at the end. That was just, that was so cool.
The greatest animation ESO has ever made.
That was pretty awesome.
Yeah, I really liked this one.
Yeah. All right. Well, thank you again, Amy, for spending some time with us this evening. It was great, and you're a great presenter. So, thank you again very much. And okay, and so now we get to our own members giving little talks and chats. Derek, are you ready to go into astrophotos and sketches from our members?
Yes, I am.
All right. Take it away, Derek.
All right. So we are about to get started with astrophotography of the month. Now, if you are mentioned and you are interested in sharing your information about each of these images and sketches that you've done, I'll go ahead and have you asked to talk. So I'll give you the opportunity to unmute yourself and allow us to hear about your work. So we're going to go ahead and let me just get my PowerPoint presentation together here. So, all right, so here we go. Now, the first one that we're going to look at here is we are going to take a look at an image I took recently over at the Everglades National Park. This was out in the middle, literally middle of nowhere in the middle of the park, located kind of basically in essentially the river of grass, as they call it. So this is a shot of the Milky Way I took in March during my travels with my wife over in the Everglades. I actually, the clouds were kind of coming in and out, and I actually thought they'd add some really cool drama to the image. This is, again, located near the Mahogany Hammock area, but it's actually out in the middle of the sawgrass area there. So again, kind of, I wanted to get that classic Everglades look to my shot. So the name of the shot is called River of Grass, River of Stars. The image was taken with a 24 millimeter Rokinon lens using a Canon 6D cooled camera. This was a shot of 2 1-minute exposures, one for the sky tracked and the other one untracked. And then what I did is I took the 2 shots and blended them together. That's a technique that people use now with to get really nice still stars at the top. You take a tracked image, you turn off the tracker, you then take a picture of the ground, and then you blend the 2 together to get not only a really nice crisp ground, because obviously if you're using a tracker, you're gonna make the ground out of focus. So that's a technique, and this is something that I definitely would be happy maybe in the future to provide a tutorial on. It's definitely a great technique to really enhance your astrophotography. The next image is from Bob Santillana, or make sure I'm saying that right, Bob. I apologize if I'm butchering your name, but I'm going to go ahead and allow you to talk, and you can talk a little bit about this image that you took recently. I'm not seeing my mouse. There we go. Okay, Bob, if you're available to chat, I have unlocked the talking for you.
Okay, can you hear me?
Yes.
Okay. This is an image I took at the Matanzas National Monument over by St. Augustine. And it was earlier this month as we're just getting into Milky Way season. I'm actually a newbie to astronomy and astrophotography, and just real excited about the whole process. This particular image was taken with Canon 5D Mark II and a Rokinon 14 millimeter 2.8 lens. And it was finished in camera raw. I believe the exposure on it was 4000 ISO with a 25-second exposure.
All right. Yeah. So I was always interested in the Fort Matanzas area, and obviously the sky doesn't look too bad from that location. So I'll definitely have to check that out.
Yeah, it's a very, very nice location.
All right. Well, thank you so much, Bob, for that information. All right. Our next image is from Bill Castro. This is one of his recent sketches. And I'm going to go ahead. Bob, you're already a panelist because you're one giving a talk. So you can go ahead and unmute yourself now and tell us a little bit about this image here, or sketch, I should say.
Yeah, this is a, you can see the details below, 3 fields of view through my 11-inch scope of Markarian's chain. You see M84 and 86 are on the far left, and it goes all the way through. Now this was done in my light polluted backyard in Oviedo, so it kind of goes into what I'm going to talk about later. You can see stuff in light polluted skies. And now there's probably half a dozen or more galaxies that aren't there that I would probably see if I was in a darker sky, but you still see stuff.
All right. Yeah, absolutely. I mean, you definitely were able to get that that series of galaxies, which is quite impressive for the location there. So thank you so much, Bill, for that image or sketch. The next we're going to talk about is from, I believe, Frank Kane. So let me go ahead and make you allowed to chat. So here you go, Frank, if you want to go ahead and talk a little bit about your image here.
Yeah, this is the Leo triplet, or the Leo trio, whatever you want to call it, in Leo of all places. M65, M66, and NGC 3628, I think it is. This represents about 14 hours of exposure time over a couple of nights from my driveway. And one thing that I was trying to achieve there was capturing that tidal tail down in the bottom lower left corner there of NGC 3628. So barely visible. It's a tough thing to catch, but I managed to catch it. So I was happy with that. This was about a 1 degree field of view. These all fit within, taken again from the driveway with a Mach Newtonian 190 MN telescope and a Paramount Mighty Mount and an Attic 383L Plus camera.
All right, fantastic. Thank you, Frank, for that. All right. All right, so there we go. All right, we're going to go ahead and make our way to our next next image, and I believe we're going to finish it off today with Richard Wright's image. So,
okay, thanks, Derek. So this is M13, the great. Well, no, it's the black hole.
Oh, sorry. For some reason, my mouse is giving me a lot of weird issues. So there we go. All right. I think it's because it's switching back and forth, back and forth. All right. Weird. It says screen sharing has failed to start.
Uh-oh.
Uh-oh. Weird. Doesn't, uh-oh. This is not good. Not good. Let me try again here. There we go. How we?
I was about to say, I might have a copy of this on my computer if you couldn't get it going. So M13, great globular cluster in Hercules. This is one of my favorite objects to look at visually. I just really love it. This is it's not necessarily my best M13 ever, but I wanted to show it. I actually shot it more or less by accident. Because of my some of my work, I was actually just kind of stress testing a new camera plugin and driver for an embedded computer thing that I work on with Software Bisque, and I need to let the scope run all night. So it's Galaxy season, and I just thought, oh well, there's M13. I'll try that. So this is an hour and a half of M13, and one of the reasons I wanted to show it to people was. It's only 1 minute exposures. So I wanted to take lots of exposures. Again, I was stress testing the camera, but it's a nice demonstration that even under light polluted skies in Lake Mary, because this is my backyard over by the middle school and high school in Lake Mary, where as long as you get plenty of exposure time, you can actually get away with short exposures. You just take more of them and you stack them together. I don't know that a really faint narrowband image I could get away with such short exposures, but globular clusters are great targets under light polluted skies. I've shot all the globulars I can get to from my backyard that my neighbors trees will allow for my globular cluster catalog, and I've been able to get a very fine image of every globular I've wanted. From this location, so they stand up to light. This is also no light pollution filter either. It's a one-shot color camera at f7, so it's not like super ideal. But again, globular clusters work out really well. And yes, Bill, I did catch that the little galaxy up there at the upper off just a little bit to the left of center. And that's how you know whenever you see a globular cluster that you're looking at M13, you can see that galaxy they got there. And I don't have the mouse, and the JPEG artifacts may have killed it, but there's also another little tiny little galaxy off to the right, and it does show up in my version of the image. But anyway, globular clusters, great targets for light polluted skies. I also, as a diehard astrophotographer, don't mind admitting that I think globular clusters look better in a large telescope than they do in photography. Can't say that about galaxies and a lot of nebula, but I just think they're fantastic to look at through an eyepiece. They have a very powdery snowball feel to them. They're just beyond gorgeous. And I think I've talked enough about this picture. So Derek, you can stop, and I actually am up next for a minute on the moon. So I'm still going to be blabbering at everybody, but only for a minute. It is called A Minute on the Moon. So let's get my keynote going here. This month, we're talking about Clavius. So Clavius is a big crater located, it's almost directly south of Tycho. This image of the moon is rotated a little bit, so it looks kind of like to the lower right, but it is directly south of the crater Tycho, which is that big crater at the bottom with the ray system coming off of it. I call it a bullet hole in the moon. Here's an image of Clavius with LRO, or the Lunar Reconnaissance Orbital data. North is up. And it's a fairly large crater, 144 miles wide. It's a little over 2 miles deep and contains several other very prominent young craters that are really cool to look at in a telescope. Their main crater is estimated to be 4 billion years old. It's actually one of the oldest features on the moon that we know about. Of course, unless you're in a spaceship, you're never going to get this view of the crater. We look at it from Earth. You can actually see Clavius from Earth naked eye. At first quarter, let me get my mouse over here. At first quarter, this right down here shows up as a notch. In fact, in one of my lunar sketches that I showed several months back, there was a notch, and I called it Tycho. I was like, well, that's got to be Tycho, because Tycho is this great big crater, but it's not. Tycho is actually this crater here above it, and it is down below. Clavius is actually much bigger than Tycho. Here's another image with lunar sunrise a day or two later. A little bit higher resolution image that I got a different time. And one of the nice things is that people like about Clavius is this little arc of tiny little craters from big to small that goes around. The bottom is called Rutherford, and then these smaller ones inside are lettered, Clavius D, C, N, J, and A. Clavius is also a really cool crater in sci-fi and literature. For sci-fi fans, it was the site of the Lunar Administrative Facility in the movie 2001, A Space Odyssey. And it's also the location of Tranquility Base Hotel and Casino in the Arctic Monkey song 4 out of 5. So there's some homework for you to go for. And I'm out of time. That's a minute on the moon. Thank you very much. And I'm done. Next, back to you, Derek. Take it away.
Do we want to do the commercial break on the vaccination now, or wait till after?
Let's talk about, I should have mentioned that at the very beginning. Since you're talking anyway, and it is your college, why don't you prequel your talk on Pluto with a little announcement about vaccination availability?
Yeah, so the Seminole State College is a host site for vaccinations, and we definitely want, this is available to anyone over the age of 16. So basically, the dates for that coming up, there's 2 dates where we'll have a mobile vaccination station at Seminole State College. This is April 23rd and April 24th. That is a Friday and a Saturday. Let me get the exact times of that. For April 23rd, this is going to be from noon to 7 p.m. And Saturday, it's going to be on April 24th. It'll be from 9:30 a.m. to 4 p.m. Now, where this is located on campus is in Building C of the Sanford Lake Mary campus. This is just to let you know, this is for those that have been a member of CFAS for a while. We used to actually have our holiday gathering in the C building, which is located kind of where the bookstore used to be. But either way, you have to book an appointment. And what I'm going to do here is I'm going to go ahead and after my program is done, I will put in the chat a link to set up an appointment at Seminole State. It's very, very quick, very fast. Wait times are pretty much, non-existent. I think you have to wait longer just to, after you get the vaccine, because they need to make sure you don't have a reaction. So definitely, if you don't have the vaccine yet, or if you have anybody over the age of 16, please take in consideration about getting this vaccine. And as I said, I'll go ahead and I'll send you to all the link to schedule an appointment after my program. So let's go ahead and get started with the mini program here. I'm going to go ahead and start sharing my screen. All right. So This program I'm going to give, I actually did this program several times in the past, and it's been a lot of fun. So I figured this would be a great program to share with you all. Rest in peace, Pluto. Now, I am a big fan of nerdy t-shirts. I think nerdy t-shirts are fun. But sometimes some of these nerdy t-shirts, well, they kind of have some misinformation. For example, this, rest in peace, Pluto. What does that mean? Does that mean that we literally blew up Pluto? Does that mean that Pluto has died after 2006? Can we not see Pluto anymore? Is this just not a thing anymore? Well, again, rest assured, Pluto is still there, still an amazing world to explore. But when I see t-shirts like this, it does bring up a little bit of an alarm in my brain going, what are we teaching with these shirts? They claim to be nerdy t-shirts, but in reality, what is this deal with Pluto? As an educator, as somebody who runs a planetarium and also teaches courses and classes, and I deal with schools, this is a question that's brought up not only from children, but a lot of times from adults on this whole thing about Pluto. So we're going to go ahead and take a look at some of these misinformation. And then we're going to take a look at another fun little thing that I wanted to talk about real quick. But here we have, this is another, I've seen this print on another t-shirt. So this is another one. I decided just to use the image here, but you can see there's the sun. Taking a picture of the family of solar system, right? We have Venus, we have Mercury. And by the way, these planets look some of them, you can't even tell which one's which, can't tell which one's Mars, can't tell which one's Uranus or Neptune and so on. You can tell what Saturn is with the ring and Jupiter, but there's little Pluto. Look at little Pluto. Aw, poor little Pluto. He's no longer part of the family. But then I start thinking about it and I say, from a planetary science point of view, from somebody that somebody who studies the solar system, why is Pluto? Why is this the case? Why don't we have QR, Sedna, Haumea, Makemake, all these trans-Newtonian objects, comets, asteroids? Why aren't they part of the big family tree? Why is Pluto? This is where, when I see these things, I start to wonder: are we really? I know it's funny, but is this really the right thing to promote when we deal with astronomy? Well, where did this whole Pluto no longer being a planet thing really start? Well, back in 2006. This man named Mike Brown. Basically, he's a planetary scientist over at Caltech. And he is a really, really good expert in especially trans-Newtonian objects and objects beyond Neptune's orbit, looking farther out into the Kuiper belt and, of course, the Oort cloud. Well, he was the one that basically said, "Hey, we are going to essentially recategorize Pluto. We're going to get Pluto." We're going to remove Pluto from the official 9 planets in the solar system. And Mike Brown is not shy about this. Mike Brown has this is his Twitter page, and that is his cover for it. It literally shows Death Star blowing up Pluto. Even his handle is @PlutoKiller. He takes extreme pride in being that person that gloats about the idea that Pluto is no longer part of the official main planetary bodies in our solar system. But is that really true to say? Well, basically, what happened here is this. The real true story of it is it was not NASA that eliminated Pluto. Actually, if you talk to a lot of members of the general public, they'll ask you, why did NASA get rid of Pluto? Why did NASA destroy Pluto? Why does NASA say Pluto doesn't exist anymore? And you get t-shirts like this that say, "Dear NASA, your mom thought I was big enough to love Pluto." The problem is NASA has become the official or unofficial, not official, the unofficial scapegoat of anything about space. Anything, whether it be good or bad. We discovered black holes. We landed things on Mars. We blew up Pluto. NASA has everything to do with it. There's no other space organizations in the world other than NASA. But it actually is not NASA that was the one that, essentially got rid of Pluto, or in this case, recategorized Pluto. It was actually the International Astronomical Union. This is the only organization in the entire world that can officially, define a planet, recognize a region in the sky as a constellation, even essentially designate stars, asteroids, all kinds of things that are in the sky that we observe. So, again, of course, that's another thing too, is those name a star programs really are not official. They are fun. They're, you can send one to your friend and, have fun of it and things like that, but it won't be officially designated. The International Astronomical Union did that. So in a committee, the International Astronomical Union, in terms of the Committee for Designation of Planetary Bodies, agreed as a committee to basically recategorize Pluto as a dwarf planet. And Mike Brown also was the one that discovered Eris, as well as some of these other objects beyond Pluto's orbit. And actually, it was Eris, which was the one that talking almost 10 billion miles away from the sun, was what kind of sparked this question of, is Pluto really a planet anymore? And what the committee looked at was they scrutinized all the aspects of what defines as a planet. Well, right now, the current definition of a planet is an object that A, orbits the sun. Pluto technically qualifies as that. B, it must have enough mass with a gravitational attraction to produce a round shape. Well, that is or spherical shape. That is also, Pluto qualifies for that. But the third qualification is what essentially makes Pluto no longer classified as what we would deem as a major planet, and now as a dwarf planet, is it hasn't cleared its path of space debris. Now, the orbit of Pluto is about 256 years or so, and it just doesn't have enough time in its orbit to have cleared out all of this excess space debris in its orbit. So at this point, well, what happened the committee decided that this was the definition of what planetary bodies are defined as. So now we're going to recategorize Pluto as a new group of objects called dwarf planets, which include Pluto, Eris, Haumea, Makemake, and Ceres, which in a way, all those objects all share those same characteristics. And another interesting thing is that Pluto, as much as all this controversy, in terms of its classification or its name, we have discovered some really amazing things about Pluto. The New Horizons spacecraft flew past Pluto back in 2015. There it is right here, about the size of a piano. And in fact, we've actually learned more about Pluto than we have both on Uranus and Neptune. And this, of course, is a false color image of Pluto, but you can really see some of these really amazing details on this dwarf planet. We have, of course, the Sputnik Planum, this large frozen nitrogen glacier. We have the Norgay and Hillary Mountains, which are basically large mountains as tall as the Rocky Mountains made up of solid water ice. We even have this tar-like material called tholins, which is a composite of organic molecules, which is said to be that where comets actually contain these tholins, and have essentially brought these things like tholins to possibly places like Earth to help for the development of life. So the ingredients for life can be found on places like Pluto. There's even a large, what we call cryovolcano, a large volcano that has erupted, frozen nitrogen into the atmosphere. It vaporizes, and basically Pluto has this nice, beautiful nitrogen atmosphere to it. So here's some of the more close-up images. We can get a really good look at that that Sputnik Planum there. We can look at the also large mountain ranges. We also find that Pluto has an active core. We find that due to the fact that it shares its rotation and its interactions with the moon Charon, it's actually causes a lot of movement deep inside, and we actually see uplift and other types of events that occur on Pluto. Again, here's some more up close images of those mountains, the Norgay Mountains. This in particular here, you can see that uplift of ice. So I think it's actually really incredible that we have all these really detailed images. This is a closer image of that Tholin region, particularly. This is called the Cthulhu Regio, which I think is a really cool name for it. If you're an H.P. Lovecraft fan, again, containing that organic tar-like material, which we think could be where we see the ingredients of life that eventually might have made its way to the inner solar system through comets and other objects. And of course, because of the nitrogen that gets spewed out from these cryovolcanoes, you get this nice, rich, beautiful blue atmosphere, similar to what we have here on Earth. Our atmosphere is predominantly a nitrogen, and that's what, of course, gives that color as well. Before we move on, I want to talk a little about another analogy that I've used about classifying and talking about Pluto. Especially for those that do outreaches, this might be a great way to discuss it. One of the things that you can bring up is that think about a library. When you go to a library, librarians will classify books based on their genre, based on their characteristics, right? So you have mystery books, you have fantasy books, science fiction, you have nonfiction, you have all these different categories, right? Well, imagine a librarian discovers a book that kind of is a blend of all different kinds of things. And that librarian doesn't really know for sure where to put this book. It could belong in the fiction section. It could belong in the nonfiction section. It could belong in the sci-fi, whatever it is, science category. Well, let's say it's mostly fiction. So at this point, the librarian decides to just put it in the fiction section. But let's say eventually in a few years, this librarian discovers a whole new group of books that come in that share those exact same characteristics. Does that librarian put those books in the same category? Or maybe there's enough books of this type of new style of book that was brought up and creating a new category. And that's essentially what we did with Pluto. What we did with Pluto is we essentially created a new category that helps us build a better view of the solar system. And even so, the word planet has become synonymous to things like mammal. Is it a dog? Is it a cat? Is it a pig? Is it a human? Well, the word planet is even a very broad word. Now we have rocky or terrestrial planets. We have gas planets, ice giant planets. We even have dwarf planets. So in reality, these planets are all unique in their own way. So Pluto, did it go away? No. In fact, we've learned more about Pluto, and I think it's pretty cool that Pluto's there, and now with a whole new group of different kinds of objects. The last thing I want to talk real quick a little bit about is this planet here. We all know it. We all love it, and it's been the butt of many jokes for many, many years, and that is Uranus, right? Uranus. And of course, many of us call it Uranus, but in reality, you can call it Uranus, you can call it Uranus, or you can call it by its real true phonetic way, Uranus, which is technically the proper way of saying it. That is because Uranus is technically part of this Greek lineage of gods and goddesses. But essentially, we've had jokes about it. Did you know 63 Earths can fit in, Uranus, or, if you want to use the word, right? Well, essentially, where did its name actually come from? And believe it or not, it actually started out with the discovery of the Herschels. And I actually got a chance to visit Herschel's home in Bath, UK. And there's a replica of the telescope that was used to discover Uranus. And in fact, Uranus was not known to the ancients. Of course, we have the 5 wandering objects, the 5 original classical planets, right? And Uranus was discovered with the use of a telescope by William Herschel with the aid of Caroline Herschel. And well, at the time, William Herschel wanted to come up with a name for this new object, this new planetary body, and he decided he wanted to call it the Georgian star, or George. Well, you got Mercury, Venus, Earth, Mars, Jupiter, Saturn. George doesn't have the same ring to it. Later on, eventually, a group of astronomers, especially in the Astronomy Royales, eventually, and several other astronomers agreed upon the use of the lineage of with the word Uranus. Now, actually, Uranus is actually not a Latinized version. Of course, Mercury, Venus, Earth, and so on are Latin names of these Greco-Roman gods. But Uranus is actually the father of Saturn, or in this case, Kronos, which is the Greek interpretation. And then Kronos was the father of Zeus or Jupiter. So the idea of where Uranus got its name came from the fact that it was broken up into the earlier creation myths of the Greeks, where Uranus was the father of Saturn and Saturn was the father of Jupiter. So that's kind of where the delineation happened. So I thought that was just, you know, a fun little interesting thing about this planet. Always gets a lot of a lot of jokes, a lot of ha-has from kids. But in reality, why do we call it that, right? Why did somebody decide to call it that name? But in reality, the phonetics of that word have changed and evolved. So is it Uranus? Is it Uranus? Is it Uranus? It's technically all three. But I guess astronomers decided that Uranus is a lot less gives a lot less issue when it comes to, you know, making fun and all that. But anyway, so that's a little presentation that I gave here. It's a little bit more abbreviated because it's a mini program, but thank you so much. And I'm going to go ahead and bring it over to Richard, and I'll post that link for the vaccinations in the chat. Thank you so much.
All right. Thanks a lot, Derek. That's another hot topic. If they're not asking you about black holes, they're asking you about Pluto. Okay, so our next and last presentation for the evening is going to be about stargazing in the Orlando Nebula by our own Bill Castro. Bill, are you ready to roll? If not, I can kill time. I can tell Pluto jokes.
Yeah, I'm
okay, good.
ready.
Everybody is saved. All right.
Yes.
Take it away.
Okay, share my screen. Trying to host disabled participant screen sharing.
Made you a co-host, Chris. Bill, you're good to go.
Okay, share, and let me get this going. Oops, don't want that one. Like I say, I fat fingered it, but he was using the mouse. All right, so this is stargazing in what I call the Great Orlando Nebula. It's also known as Orlando Skyglow in urban astronomy. Well, you've got a new telescope, and what can you see with it? Or like most of us, we haven't been getting together and going to dark sky sites like we used to. Sadly, not all the Messier objects are visible in most backyards. So I'll discuss what objects you can see and how to make an observing list for your backyard. It's primarily for members new to astronomy, and experienced observers will benefit from some referenced observing lists at the end of the presentations, and you're encouraged to add some of your own. And for obvious reasons, the moon and planets are not discussed here. You can see those almost anywhere. So for better or worse, this is us. This is a screenshot of a web page. You can see the URL up on top. And that is the Bortle scale. And it's got different colors for different areas of light pollution intensity. The white and gray, hopefully you can see my mouse. That's Orlando itself. That's a class 9, Bortle class 9 inner city sky. Naked eye limiting magnitude, that's what NELM stands for. It's less than Mag 4. Now the red is transitioning into the near suburbs. You can see Kissimmee down here. Winter Gardens right here on the edge. Sanford is up here. I'm in Oviedo. I'm probably about around in there. So that's listed as a Mag 4.5 sky. That's a little bit generous if you ask me. I've noticed light pollution getting worse over the years. And the orange or brown is listed as class 7 with the Mag 5 sky. It's a little further away from Orlando. But as we'll see in the next few slides, it's a lot of red, but not all is lost. There we go. And so in spite of this, stargazing is still fun to do. The most important thing, no matter where you're at, is to know what you're looking at. Now these images of M27 you see in the bottom were taken with a Steadicam video camera. It's got a 2-second integration time. And I grabbed some frames on those through different telescopes. But it shows the same thing you would see with your eye through the eyepiece. That's kind of giving you an idea of what you can really see through the eyepiece. And what these images show going from left to right is either with a darker sky, a larger aperture, and I'm a fan of aperture, and or better seeing conditions, you'll see more detail in many objects. But the object's still there, you know, it's not all lost, it's still there. And the neat thing is you can see the object. I mean, these photons travel billions and billions of miles to get here. We can't let them down, we gotta watch them. So in my backyard in Oviedo, I use notes a lot. And for my observing notes, I use a scale of 1 to 5. That's relative to my backyard for my seeing and transparency. So that means, you know, what I can see on an average night, I'll see a mag 4.3 sky. On a good night, it's 4.5 and so on. I'll note that naked eye limiting magnitude. I'll also note, you know, the temperature, the relative humidity, and the dew point temperature. I keep all of this for future reference. So this helps me get a feel for what's visible under what weather conditions, you know, when to try something or when not to. You know, and the Orlando Nebula is to my west. The Andromeda Galaxy, the Beehive, and the double cluster are visible naked eye, if you know where to look for it. And they are in the dark part of the sky. So for me, that's overhead and to the east. And you can see in the upper right, I use a 130 millimeter refractor, which is like a 5.1 inch scope. And I have an 11 inch Smithsonian. You know, go-to mounts are helpful, but not really needed. I have both go-to and a simple clock drive mount. And the important thing is go out and look up. So making a list, you know, you want to note the magnitude and size of the object. The magnitude is given for all the light from that object condensed into a single point source like a star. And you want to note that in your observing log as you go. You know, for example, M32, it's a Mag 9 galaxy that made the Astronomical League's urban program. And that's shown on the right. Here it is up here. This is a little screenshot I took of it. And there's M32, you see Mag 9. And it's pretty small. And you can see it in the image below. There's M32, this is M31 next to it. But that's what I would see in my 5-inch refractor. Oh, excuse me. Now you think M33 and Mag 5.8, you know, would make the list also. I can't even see that in my 11-inch scope. It's a much larger object. You can see 62 arc minutes by 37 arc minutes. So it's a much larger area and it has low surface brightness. That's the key word there, low surface brightness. And that's not always listed on these observing lists. Now it's M31, it also has a bright core. I can see it, but I can't see the surrounding spiral structure. So in your observing notes, it's important to note what you can see and what you cannot see. And all of these observing notes over time will help you gauge your backyard and your optics so you can pick out objects for your next list. It helps you as you go along. So what can you see? The galaxies, nebulas, and globular clusters, they follow that magnitude and size rule of thumb. You know, there's a few exceptions if it has a bright core or not a bright core, things like that. But open clusters, excuse me, have the added constraint that there's a field of stars. The biggest issue is if you can see the individual stars inside that cluster. I've got two examples of that here. NGC 7789 is on top. It's a Mag 6.7 and 25 arc minutes across. And then below that is NGC 457. That's the OWL or ET cluster, or Dragonfly cluster. It's on the bottom there. That's pretty close. It's mag 6.4, 20 arc minutes across. The key thing is in the top image, that cluster has stars are mag 11 and fainter. I need the 11-inch scope to see it. I can't see it in my 130 millimeter refractor, but I can see 457 in my 130 millimeter scope. There's not as many stars and they're a lot brighter. In fact, that object's great in just about any scope. I could pick it up in my binoculars in my backyard even. So a lot of it is just try it, see how it works. Your mileage might differ. So I've listed where to get ideas here, and it's kind of my go-to place. The Astronomical League has an urban observing program, and club members are all members of the Astronomical League. Even if you don't want to go for the award or the pin, you can still download the list. And there's two lists that it has, one for deep sky objects and has a D right before the period on that URL. Then the other is for stars. It's got a handful of double stars, and I think algo also is a variable you can watch. It has an S there. Sky and Telescope has 111 deep sky wonders for light polluted skies. You can see that's available online. Now this one, the Saguaro Astronomical Club, that has observing lists galore, and some of you experienced observers might want to check that out if you haven't already. They've got over 30 lists and programs, all various, there's something for everybody. Now they have, you can scroll down to get the urban list. They're out of Metro Phoenix. So if you can see it in Phoenix, probably similar light pollution to what we have here. And that's their URL. Astronomy and Sky and Telescope magazines, if it's on their all sky charts in the middle, you'll probably see that in binoculars or a telescope. And they'll have articles for small scopes as well. The Royal Astronomical Society of Canada, the Observer's Handbook, that's up here. That was mentioned earlier. There's still two for sale. And I recommend that to anybody. You don't need to buy one every year. Just get one, hang on to it. It has a bunch of different lists, something for everybody also. 70% of the information there is pertinent from year to year. Telescope math equations, observing tips, so forth and so on. And these two books at the bottom, excuse me, Celestial Sampler has 60 star hops that Sue French uses I think 105 millimeter scope or 4-inch scope, and binocular highlights. If you can see it in binoculars, it'll look a little better in a telescope as long as it fits in your field of view. So, any questions? Just remember, the object's still there. It's important to see to know what you're looking at. Surface brightness, it's all about that. Observing notes help, and just give it a try. So with that, open it up to any questions, or anybody have, observing lists or recommendations on your own. You can bring it up now, or you even put it on the group's IO page.
Okay. Well, thanks, Bill. That was great. I want to encourage any of our members to, if you want to give a presentation or a mini program, we would love to have it. Bill's done a couple now. He's got another one already on the slate for next month. I'm very excited about myself. That is the end of our CFAS program tonight. Thank you, everyone, for your time and your faithfulness while we're on Zoom. We do hope to be meeting again as soon as we can when the world and everything allows it. it'll be great not just to go to dark sky sites, but just to meet in a parking lot again and set up some telescopes and hang out for a while. I usually make the joke that nobody in my family understands club. It's a great it's also a great social experience as well, and I really enjoy it. So everybody have a great week. We meet again on May the 14th on Wednesday. Stay safe, wear a mask, get vaccinated, and I will see you then. Bye-bye. Bye.